Hey, how'd those two problems go? Or three problems? Or four problems? Was it two of them? Was it 10 and 11?
Yeah.
How'd it go?
I see both so much. Yeah, and at the same time.
One more time. That's much better. But that's the one we wanted. Alright. Nope. Alright, so let's take a look at those two problems. See how we did. Let me correct my attendance while I can. I think we're good. Alright, so let's review real quick before I get into these problems. So, when I take derivative, does that find me the slope right away? Hey. Yes or no? No, why not? Because it doesn't. You can't find the derivative right away because you don't know what the slope of the tangent line will be. So, basically, when you find the derivative, if you had something that looked like this, you have an infinite amount of points. So theoretically, there's an infinite amount of tangent lines that would go along this curve. Okay, so I don't know what the slope is until I do what? Find the derivative. What would find you the slope once you find the derivative? What do I have to plug in? So like this line right here has a different slope than, say, this line. Agree? And this has a different slope than this line, and this has a different slope. So I have to plug in whatever the x value is at those particular points to figure out what the slope would be. Okay? So you take the derivative. That'll allow you then to plug an x value in to find the slope. The derivative will show an awful lot of things, and we'll get to that after spring break once we start getting a little further into this. But so if we took a look at number 10, and I'm on what? Worksheet 4.3? Is that right? So we looked at number 10. It says determine all the x values where we have horizontal tangents. So we're looking for horizontal tangents. So that's when f prime at x is equal to 0. So here's my original equation. Okay, and I'm going to show you how this is going to work. This is going to play a little bit into it. So if I find the derivative, I just put f prime. If you take a regular calculus class, you go through the whole process of doing a derivative where you plug x plus h in minus the original function all divided by h. But the shortcut way, so what's my derivative going to be? What's the derivative of x to the fourth? 4x to the third. What's the derivative of this?
Negative 12x to
The second. Cool. And the derivative of this is just 0, so we don't even have to worry about it. Agree? Alright. So, now we want to figure out where our horizontal tangents are all equal to 0. Meaning, where do I have a line like this or a line like this? Let's say those are both horizontal. So those are horizontal lines. So what we're going to do is we want to know where this is equal to 0. So if I go 4x to the third minus 12x squared, and I set it equal to 0, and then I use a little bit of algebra, and I say, oh, look, my greatest common factor is 4 and x squared, and then I get x minus 3, set those equal to 0. I get 4x squared equals 0, so x equals 0. So at 0, I have a horizontal line. If I set this equal to 0, so at 3, I also have a horizontal line. So basically, if I looked at an xy axis, at 0 and at 3, the graph itself is going to have a horizontal line. It means it's either at a local min or a local max. Okay? So this could do something like this. Or no, that's not it. Do something like this. Something like that. Or some iteration that takes place. That's actually not it, but you can draw. Okay? And then write the equation of the tangent line to the curve at the indicated point. So number 11, we have this equation, and we want to figure out at x equals 4. So we're trying to figure out what the equation of the tangent line is going to be. So I could do one of two things first. Because I want to find the equation of the line, I need to figure out a point off the original. So if I take 4 and plug it in, I'm going to get 5 minus 2 square root of 4, 5 minus 2 times 2, 5 minus 4. So at 4 comma 1, this is going to become my x1 and my y1. So we're going to save that for a moment. I then need to modify my equation to look like this. X to the 1/2 power. Okay? So I have not taken the derivative yet. I've just converted it into having a fraction of an exponent rather than dealing with a radical. If I take the derivative, y prime, the derivative of 5 is 0. The derivative of this is going to be negative 2 times 1/2. And then x raised to the 1/2 minus 1. So my derivative cleans up to negative x, because that cancels to become 1. Keep the negative. And then make that 2 over 2. So I get to that point there. Okay, you got to go back and kind of remember Algebra 1 for the most part, or if you don't want to convert this, then just realize I'm going to take this original 4, plug it in. So I could go to Desmos and easily plug that in. I could go, get rid of statistics, I can go negative 4, parentheses, or negative 4, I don't need the parentheses there. Then I'm going to go raised to the parentheses, oops, raised to the parentheses, negative 1/2. So you get negative 0.5. So this gives me negative 0.5. Negative 0.5 is the slope. And then I can jump into y minus y1 equals m times x minus x1, which is called point slope. Plug in. Remember, when you plug the x and the y, it becomes opposite sign. X minus 4. So this equation here, this linear equation here, is the equation of the tangent line at the point 4 comma 1. That's what our linear equation would be. Okay, so it would just kiss it there. And if you wanted to dork out to this a little bit, why not? Because I have Desmos. If I were to graph y equals, if I were to graph my original equation, I'm going to get 5 minus 2 square root of x, can go hit home on that. So that's what it basically looks like, and then if I graph my other equation, y minus 1 equals negative 0.5 parentheses x minus 4. Okay, so here's our point 4 comma 1. So that's this equation here. At that point, that purple line is tangent to the green equation. It has a negative slope to it. Means the equation is decreasing there if you wanted to go with some calculus terminology. But that, for the most part, is how this is done. All right, so I want to show an example that you don't have to write this down, but let's say I have y equals 2x to the third plus 7x squared minus 4x plus 5. Okay? So, pretty simple equation. So I want you to see what the derivative graph next to this. So if I take the derivative of 2x to the third, what do I get?
6x squared.
6x squared, very good. If I take the derivative of 7x, what do I get? Or 7x squared, what do I get? 14x? And then what if I take the derivative of negative 4x, I get just negative 4. And this becomes 0, okay, as a derivative. So if I graph the two of these together, the derivative shows certain characteristics to your graph that you might not be aware of, because there's times they will give you the derivative and say, hey, what does the graph look like based on that, whether it's above or below. So I'm going to go y equals 2x to the third. So y equals 2x raised to the third plus 7x squared minus 4x plus 5. And if I hit home, this is basically the main foundation of what our graph looks like. The x-axis in there too. Okay, so this is what our graph looks like. If I graph the derivative with it, I'm going to get y equals 6x squared plus 14x minus 4. Okay. All right. So the derivative, as I go between here and here, this x value up here corresponds with this x value up here. This x value here, or we're across the x-axis, so let me actually tap on those. So the red crosses here and here. So notice the two x values that are at those 2 points. If you click here, so that means that's where, thank you very much.
Yeah, of course.
That means that the x value at the peak here, this x value should be the same thing. So the big notice is I get negative 2.591, I get negative 2.591. So the maximum here becomes the 0 of the derivative. And that means that the minimum value here should have the exact same x value as this other one. So this 2.57 and this 0.257, they are the same, but notice this is the x-axis here. So the derivative gives you information about what your graph has done. So if someone were to say, you know, hey, is our graph rising or falling, but here's our derivative. What does the original graph do? That's where you could say that you'd either have a positive slope or a negative slope. The slope of where it would be 0 of our tangent line would happen at the local mins and maxes. When those local mins and maxes take place, that means that's where it's crossing the x-axis. So that's basically what I got. Cool. All right. So because I am not sure what the next 2 days will bring, I don't necessarily want to go further. I want to just kind of like ease us back. So that way, when we get back from, if we don't have class tomorrow, that's fine. I do have a quiz that I was planning to do tomorrow, but if we have the next 2 days of snow day, or if tomorrow's a snow day and the rest of you decide to take Friday off, because why not have an extra 2 days for spring break, which I don't blame you. I think I might be that person as well if I was in high school. When we come back from break, we'll have a review on like probably Monday and Tuesday, and then Wednesday we will do the quiz on derivatives. It's a pencil paper. I'm sorry I don't have it on Schoology because I actually wanted to see some work. But that's basically. Do you guys have any questions about what we've been doing with derivatives so far? I mean, we've kind of taken the first 9 weeks of honors algebra or honors pre-calc and pre-calc. In their last 9 weeks, I condensed it into 2 days, maybe 3. So, though you don't necessarily have the understanding that what calculus is doing at this point, you're getting a basic taste of it. So that's what we have planned. So we are out of here at what? 47. So next 20 minutes is yours to kind of chill. Deal? Any phone calls coming for that?